Today we have been asked to fill in the first molecular orbital diagram below for the CO and CS sigma bonds in carbonyl oxysulfide. So we have to give the correct hybridization for each of the atoms by circling the correct choice of sp3, sp2 or sp on the diagram. That's like our first thing that we have to do. So first, basically what we will do is that we will draw out the correct Lewis structure, right? So if you draw it out using the correct rules, then you'll get the carbon in the middle, and around it you'll have oxygen and you'll have sulfur, right? Each bonded via like double bonds, and once you complete the octet, this is what you should get, and each will basically have a complete octet, right? So if we look at the hybridization for the oxygen using just the steric number, so it is the number of lone pairs plus number of sigma bonds. So 2 lone pairs plus 1 sigma bond, that's like a steric number of 3, right? And that gives you sp2, right? For the carbon over here, you have only 2 sigma bonds and no other lone pairs, so that should be sp because the steric number is only 2. And for this sulfur over here, you have 1 sigma bond and 2 other lone pairs, so this should again be sp3 in this structure for carbonyl oxysulfide, right? So sorry, my bad, sp2, because it's 3 as a steric number, right? So sp2 over here and sp over here and sp2 over here again, right? And the second is that we have to label the orbitals where indicated by A with stars on top to describe the molecular orbitals. So we have to determine whether it's a sigma star or a sigma or a sigma pi, right? Sigma or a sigma star orbital. So basically we need to know the difference between bonding and anti-bonding. Bonding orbitals are like the lower ones, right? These ones at lower energy are your bonding, and then you usually have your non-bonding, which is when you have like an odd number of molecular orbitals going into the diagram, actually of atomic orbitals going into the diagram, which will come out as molecular orbitals, right? So basically we need to know the rule that the number of atomic orbitals you put in is equal to the number of molecular orbitals you will be getting back, right? And so always, like, whatever is lower energy, that will always be your simple like sigma or pi, and the star one, which they will be your anti-bonding, and they will be at the top, right? So right now they are sigma and sigma star. We are not looking at pi and pi star right now because we're looking at sigma bonds right now. Once we start talking about pi bonds, it would have been pi and pi star orbitals instead, right? And now the next question is to fill in the arrows to show where the electrons will go in the molecular orbital. So we do that using all of the rules that we know, like Hund's principle of Bose and Pauli's exclusion. So basically they need to be in like opposite direction, right? They need to have the opposite spin, and you always need to fill in the lower energy orbitals first, right? So basically between the carbon and the oxygen, we're only looking at the sigma bond, so only this one. So this is giving 1 electron, this one will be giving another. So basically 2 electrons in that sigma bond, that's between carbon and oxygen. And between this carbon and sulfur, only looking at the sigma bond over here, this will again be, this carbon will be giving 1 1 electron, and this sulfur will also be giving 1 electron, right? So in total of 2 electrons in the bonding molecular orbitals. And that, because we always fill in over here first because they are lower energy molecular orbitals, so we fill them in first, and then we go on to filling in the higher energy orbitals, which would be your anti-bonding molecular orbitals in this case. We have to fill in the molecular orbital diagram for the CO and CS pi bonds in carbonyl oxysulfide. And firstly, we have to put the labels where it's indicated, and then we also have to show where the electrons will go in the molecular orbitals. So starting with the labels, so if we look over here, so this is because right now um, we're talking about pi bonds, right? So that means we're going to be talking about the p atomic orbitals, right? Or the pi atomic orbitals. And the lower one will be just simple p orbital, right? Or you can write it as pi instead, right? Simple pi. Or, and then over here, this one is higher energy, so you can write it as pi star, right? That's your anti-bonding pi molecular orbital. This one over here is your bonding pi molecular orbital, right? So this one is your bonding pi molecular orbital, that one is your anti-bonding pi molecular orbital. So when we're looking at where the electrons will go in the pi bonds, right? So we have to think about, like, we know that these two there's like one sigma bond each, and then there's also one pi bond each between carbon and oxygen and between carbon and sulfur, right? So right now we're only thinking about the pi bonds, so it is quite the same as the sigma bonds because there's one pi bond each. So again, 2 pi electrons between each carbon and oxygen and between carbon and sulfur, right? So and it's the same thing over here, it's the p atomic orbitals, right? Because we're looking at the overlap of the p orbitals, right? Because the overlap of p orbitals is what creates the pi bonds, right? So we're looking at the atomic orbital overlap of p orbitals to create the pi bonds. So again, because there is one pi bond between carbon and oxygen, that corresponds to 2 electrons, right? 2 pi electrons. And that should be it for this part of the question. To show how basically the sigma bonds and pi bonds you can actually show, which will help strengthen your understanding about the sigma and the pi bonds. So basically the carbon, which we know is in the middle, the oxygen is over here, and the sulfur is over here, right? So the oxygen over here is involved in one pi bond and one sigma bond with the carbon, right? So we draw the pi bonds like this, right? This is your your p orbitals for the pi bond, and this is for your sigma bond, right? This is your head on, right? So this will allow for something like this, and this will be your sigma. The carbon will have uh, 2 p orbitals, right? Each for overlap, right? So it will overlap with this one over here, and this one will overlap over here with this. So this is your one pi bond with carbon and oxygen, and the sigma bond with carbon and sulfur can be shown over here, right? And this is your sigma bond, one sigma bond with carbon and sulfur, and the sulfur over here has one p orbital, which will be in like an overlap with the leftover p orbital of the carbon. And that should be it for how you can draw out the sigma and the pi orbitals. And I hope that helps strengthen how you can determine the number of pi bonds and the number of sigma bonds. So you always only have like one sigma bond, and the rest of the bonds are your pi bonds, right? And this is how the overlap will occur. So the overlap of 2 p orbitals is basically what is creating one pi bond, right?